Module 2, Lesson 5, Linear Regression. For this module, we'll be discussing the different curve fitting techniques, specifically regression techniques. And the simplest regression technique would be the linear regression. What are the following criteria for best fit using linear regression? And how do we quantify errors under regression? And other factors that do affect our regression, like standard deviation. And finally, the coefficient of determination, or often referred to as the correlation coefficient. Curve fitting techniques are often applied in order to represent a given set of data using an equation or a model equation. In doing curve fitting techniques, you may apply interpolation, whereby your particular given set of data points eventually are fitted using a particular polynomial equation that will literally pass through every given data set on your given particular set of data. Or you may apply a regression technique, whereby your particular model equation will not necessarily pass through the data points, but rather it often follows the general trend or shape of your given data set. The least square regression is actually an appropriate strategy in determining an approximating function that fits the general shape or trend of your given set of data without necessarily matching the individual points. It is a process whereby substantial error is associated with the data, and the polynomial interpolation is inappropriate and may lead to unsatisfactory results when used to predict intermediate values that are beyond your given set of data. The least square regression is a particular technique that devises a criterion in order to establish a basis for a fit. And one way to do this is to derive a curve that minimizes the discrepancy between data points and your given curve. Under linear regression, the curve happens to be a particular straight line that will approximately fit your given set of data using paired observations. The mathematical expression for this straight line is given out by the general form to be equivalent to y is equal to a0 plus a1x plus e. Your a0 and a1 are coefficients that represent the slope and the intercept of your given particular line. Thus, similar to the trigonometric equation with the form y is equal to mx plus b, whereby your b happens to represent the intercept, which is in this case similar to your a0, and your m represents the slope, which is in this case similar to a1. Your e is what you call the substantial error that is measured based from the given model regression line and your actual data point. The difference between these values of y on a given particular value of x represents then the error. Note that the substantial amount of error may either be positive or negative, depending on where your actual data is. If the actual data is above the regression line, then your error becomes positive. If the actual data now this time is below the regression line, therefore the error now becomes negative. This particular residual error can then be represented by this equation, which is equivalent to e is equal to y minus a0 minus a1x, which eventually is simply your actual value of y minus the predicted value based from your model equation. On a multiple data or a created set of data, eventually it's also possible to create multiple possible lines that will eventually follow general trend or shape. If you're given something like this, whereby our given set of data forms three possible straight lines that may fit its corresponding general trend or shape, it becomes difficult to determine which particular straight line should be used in order to represent properly your given set of data. Therefore, there has to be some sort of criteria that is used in order to select or apply this particular regression. To remove this subjectivity, some criteria must be devised in order to establish a basis for the fit. In order to fit the given set of data into a linear function, errors or residuals on each data point must then be considered. The concept should then be a unique linear function wherein there is a minimum residual error on each particular data point. Hence, the errors should be reduced or minimized. The errors in a linear regression are eventually categorized as follows. You may use the summation of residuals or errors. Upon doing this, note that if I sum up all the errors, eventually all negative errors will subtract all positive errors, therefore ending up with a misleading slope for my respective given model regression line. Hence, this criteria is not used. You may also think that if I simply use the sum of absolute residuals, which eventually should lead into this given equation, would give me a particular straight line that would give me a minimum amount of error, since we've already considered that all errors now are positive and then summed up. However, this eventually do not create a unique straight line that will fit all your given data points. So we're simply back to our same problem. Thus, this particular criterion is not used. Hence, finally, we simply square the residuals and then sum them up, eventually ending up with this particular formula for your summation process, which eventually gives us a unique straight line that will eventually be produced from any given particular set of data. Note that this particular criteria is then affected by outliers. Outliers are data points that are usually excluded or sometimes seen to be away from our given group of given set of data. These particular outliers eventually affect your given particular straight line, since this particular sum of the squares of residuals eventually consider the error on each particular data point. Thus, since this particular criteria is then used in order to select your given straight line, then the technique is often referred to or otherwise known in some textbook to be the least square regression technique. So in order to minimize then the error, we then simply minimize this particular criteria, which is your sum of the squares of residuals. Upon doing so, you need to evaluate then the maxima minima of this given particular variables, namely A0 and A1, thus obtaining the partial derivative of your criteria with respect to A0 and the partial derivative of your criteria with respect to A1, ending up with these given equations. Note that if I transpose 2 to the other side of my equation, dividing 0 with 2 would simply leave us with 0, and then simply distributing your summation on each term found, as well as the coefficient -1 and -x1 onto your given terms. Thus ending up with this given set of linear regression function system of linear equation for A1 and A2 to be like this, and this. If you transpose all the negative summations on the other side of the equation, you would then simplify the system of linear equation and replace summation AO with NAO. Thus, the equation now becomes like this and this, ending up with a system of linear equation for two unknown variables, namely A0 and A1. And at this point, you could actually use your calculator in order to solve for the coefficient values of A0 and A1 by simply typing in these different summations and n onto your given system of linear equation. Or you could eventually apply substitution or elimination in order to solve for variables A0 and A1. When you apply substitution, you would eventually end up with a formula for your A1 to be like this, and the formula for your A0 to be like this. Note that Y bar or Y average means the average value of Y, and X bar means the average value of X. There are other factors that are often considered when doing linear regression. You often also denote standard deviation, which is basically shows us the goodness of fit of your given particular set of data onto your regression line, which is often depicted by this given formula. Note that if the standard deviation for your given particular set of data tends to be low, it simply shows you or informs you that the data points are simply clustered along your given straight line. Whereas if your particular standard deviation is high, it usually means that your particular set of data is normally scattered around your given particular regression line. And in order to solve for the coefficient of determination, your coefficient of determination is given up by this formula, whereby it's based from your sum of squares of your residuals and your standard deviation formula. You may also evaluate your SR using this concept, which is the formula for your sum of squares of residuals, and your ST to be this formula, which is your standard deviation. Likewise, you could now solve for the correlation coefficient by simply obtaining the square root of your R squared, or simply applying this particular formula in order to solve for your correlation coefficient R. Correlation coefficient R under your given linear regression usually falls between -1 to +1. Let's try to evaluate this given example and try to determine a linear regression that would eventually fit this given set of data. Note that the objective is to evaluate for a particular model function using a straight line, since we're using linear regression. Therefore, we need to evaluate then the values for A0 and A1x that would eventually fit this given set of data. Plus, we also want to check and evaluate for SR, our sum of squares of residuals, and our standard deviation in order to evaluate for the correlation coefficient of our linear function. And finally, we solve for the coefficient of determination, which is R squared and R. So all you have to do is to tabulate the results for your data points X and Y, and then sum up all the values of X, in this case, eventually ending up with a value of 28, and sum up all the values of Y, in this case, ending up with a value of 24. We then individually square the values of X, thus giving us a summation xi squared equal to 140, and then we multiply each value of X to your respective value of Y, thus giving us the product xi yi. And if we sum that out, we'd end up with a value of 119.5. We then use the following summations in order to evaluate then this linear equation. Note that these particular summations are based from our given system of linear equation that was derived earlier using our criteria. Therefore, you'd end up with an A1 value now with this solution having a value of 0.8393. Your average value of xi would have this solution equivalent to 4, and your average value for y would be equivalent to this solution equal to 3.4286. Thus, you can compute for A0 to be like this onto our given formula, which gives us a value of 0.0714. Thus, giving us a particular model function equivalent to A0, which is 0.0714 plus A1x, which is in this case 0.8393x. Note that this particular model function already incorporates your given particular error. In order to evaluate then your respective error on each of your given data point, we simply apply our model function and then substitute each value of x seen on our data set, thus giving us a model value of y, where the regression line eventually falls into. So this particular model function creates this model value of y, which then shows us how much error was actually incurred and reduced on our given regression technique. To solve then for the error, each individual point is then subtracted on your yi with your ym. That results in, this time, the difference between the actual value and the model value of y. Thus, ending up with a tabulated solution for your error to be like this. Note that the criteria for best fit is applied. Therefore, each individual error is then squared, thus giving us the following values for each of your errors. And then if you summed up all of these squared errors, this now is equivalent to your SR, which is in this case equivalent to 2.9911. After which, we then evaluate and establish for the standard deviation by subtracting from your given yi the average value of y, and then squaring its values. You'd end up with this individual standard deviation of y on each of your given particular data point. And then if you sum it up, you'd end up with a summation now equal to 22.7143. We can now use these particular values in order to solve for our coefficient of determination with this formula, thus giving us a coefficient of determination equal to 0.8683. And therefore, our correlation coefficient, if I evaluate for its square root, would simply be equivalent to a correlation coefficient of 0.9318. Note that the correlation coefficient usually determines and shows us whether how close your respective values are to your given regression function line, which can tell us if this particular regression function line can be used to predict successive values of your respective x, which are not included on your given table. Note that this correlation coefficient usually is very high. Correlation coefficients ranging from 0.7 all the way to 1 with an absolute value normally refers to a very high correlation coefficient. A correlation coefficient ranging from 0.4 to 0.6 usually is considered to be a moderate correlation. And correlation coefficient with an absolute value of 0 all the way to 0.3 normally refers to a minimum or even non-related variables. This ends then our Module 2, Lesson 5.